Hey, Chem 30s, it's Manchak here with your last concept lesson for Unit B, Electrochemistry. I'm going to record this lesson for you. I've shifted positions a little bit because I got something over on my right here that I'm going to try out and see if I can make work to give you sort of a live action shot of me going through examples. Hopefully it works. Give me feedback. Let me know how things are going. And speaking of feedback, guys, if you've got a couple of minutes to drop me an email to let me know how are things going with you. Is there too much going on? Is there too little going on? Just tell me what's up. I want to hear from you guys. It's weird just sitting here in my basement talking to a computer screen and really not knowing how you guys are doing. So, pop in and let me know what's going on from time to time. Come into the office hour that I'm putting on every day, and maybe have a quick conversation. Even if you don't have a question, I'd love to hear how you guys are doing. Like I said, it gets pretty lonely down here. I mean, I got my wife and my daughter upstairs, but they're busy doing their thing too while I'm working. So let's get started so we can get through this as quickly as possible. So just a quick few set of notes here. And these will all be listed in the Google Classroom as well as we go through. This is our last concept of Unit B in our electrochemistry unit. This one is called cell stoichiometry. And just to be clear, we're talking about cells in so much as we're talking about batteries and electrolytic cells, those kinds of things. We're going to be learning a couple of new formulas, one that we're going to use almost exclusively, but it's nothing more complicated than we've had a look at before, so there's nothing to worry about. I've got 4 examples to go through with you to show you what we're doing in this, and then you'll see down here I've got a couple of practice, some extra video stuff. This one is looks like from another teacher in Alberta, so if you are sick of my voice and want to run through it again, you can do that. And then this is actually from this link is actually from the B9 section from the last concept where we went through electrolytic cells, and it talks a little bit about B10 in there as well, so you'll get a little bit of the IT over F stuff that we're going to talk about. And then you got some formative practice. There's an LSM with some practice questions on it. I'm going to post a couple of diploma questions at some point this week. They may already be up by the time this video is up. And then a few practice questions, and then I'll give you your summative quiz, and that'll be it for concept or Unit B. And that means that next week we'll be moving on to Unit C, which is our organic chemistry unit. So I'm going to switch over to the PowerPoint, and we're going to get started on cell stoichiometry. So our objective for this concept, B10, is to learn how to calculate mass, amounts, current, and time in single voltaic and electrolytic cells by applying Faraday's law and stoichiometry. So I got a few things to introduce to you. I mean, we've already done lots of stoichiometry, and you've done some already earlier in this unit, so that shouldn't be too bad, and everybody seems to be doing fine with that. So really we're going to introduce Faraday's law and start to tie in amounts, things like current and time that we haven't really worked with yet. For those of you that have taken physics 20 and 30, I can't remember where Faraday's law falls into there. I think it's physics 30. Some of this will look a little bit familiar. I may use slightly different units than what you're used to, depending on the concept, or depending on what you learned in physics. So just be aware of that. All right, so when we electrify a cell, and by electrify, when we're actually providing electrons to it, like we would in an electrolytic cell, as in electroplating or in the refining of metals, the quantity of electricity it passes through the cell determines the masses of substances that react or are produced at the electrodes. What I mean by that is, remember, as we're running an electroplating cell, what we're actually doing is we've got 2 electrodes dipped into the same container. That container is full of ions of the metal that we're wanting to plate onto something in that cell. And I think I showed you guys a diagram in B7 in the last lesson where we had an electrode and then we had a spoon dipped in. And the whole goal was to try to plate something onto the spoon using ions in the solution that would gain electrons to turn into the solid metal on the spoon. So we're plating the spoon. We're making a silver spoon, just not, completely out of silver kind of thing. So the amount of electricity that moves through gives us an idea of how much we are going to plate, what mass of stuff we're going to plate onto that spoon or bumper or whatever it is we're doing with electroplating or electrorefining. Electrons, we know, are gained and lost in order to produce these substances with the help of electricity. What we can do is we can establish a mole ratio for this as well, for both the electrons and the reactants and products within a half cell or a net cell. I'm going to give you a little hint here. Usually what we're going to be working with in these scenarios are half cells. And the reason why we're working with half cells is half cells still have electrons in them. So you can actually find the electrons in the half cell, whether it's a product making it an oxidation half reaction, or whether it's a reactant making it a reduction half reaction. Okay, so we're going to still be looking at GR, and Leo goes GR still here, to remember what's going on in these sections. So be aware, we're usually going to be dealing with half cells. Okay. Before we can actually start to do any of that work and any of those calculations, we need to look at the amount of electrons we need for our net or half reaction. And we need to see how the charge is determined. Okay, so we're going to play around with this a little bit. And this is where, physics folks, this stuff is going to look relatively similar to stuff you've already done before. We're going to be talking about charge, which is represented by a capital Q for its variable. And charge is measured in coulombs. And a coulomb is simply is determined from taking the electric current in amps and multiplying it by the time in seconds. And that's going to give us our determination of charge that we're measuring in this case. For those of you, I'm not going to go too deep into the derivation of this because it's really beyond what we need to know at this point. But an amp is a coulomb per second. So an amp is the charge moving through a given spot every given second. And so what we're basically doing by multiplying I, which is our current, and T, which is our time, we're figuring out C. If we've got time on the top and time on the bottom, those are going to cancel out, and we'll be left with coulombs when we're done. 1 coulomb is the quantity of charge transferred by a current of 1 amp during the time of 1 second. Okay, that individual amount is not terribly large, but when we start to get into operating something for longer than a second and at higher amps, then we end up with more charge. And for those of you that have done some of that physics, you know that voltage is important to pay attention to, but paying attention to current is just as important, if not more important, because that's the stuff that can be most damaging to you. So all this leads to talking about Faraday's law, and this is just a Cole's Notes version of what we're doing here. There's lots more to this. I'm just not going to get into it at this point because it's not as important to have the background as it is to just understand the basics of this. So Faraday's law was developed by Michael Faraday, and what he was doing was studying electrolysis and identifying factors to determine the mass of an element produced or consumed at an electrode in an electrolytic cell. What he discovered, this is very important, is that mass is directly proportional to the time the cell operated as long as current was constant. So that whole directly proportional thing here, that's super, super important, because I'm going to get you guys to think back to what we were talking about in Chem 20, because we talked about the two gas laws right off the bat, Boyle's law and Charles' law. And it was Charles' law, if you recall, where we said things are directly proportional, meaning that the more, if we put more temperature into something, then the volume is going to increase, right? If we increase temperature, volume increases. If we decrease temperature, volume decreases, right? If we increase the mass, if we increase how long the current operates, the mass is going to increase. If we shorten the time the current is operating, the mass is going to decrease, the amount that we're plating. Okay, so this whole idea in here is called Faraday's law. And Faraday's law comes along with it a constant. And that constant is basically saying that 9.65 times 10 to the 4 coulombs of charge is transferred for every mole of electrons that flows in a cell. So we call that Faraday's constant. And what's really important for us in chemistry here is that we're talking about the mole here. Every mole of electrons that flows transfers 9.65 times 10 to the 4 coulombs. That mole, please remember, is really what allows us to link lots of variables together using stoichiometry. Okay, so that mole comes up again and again, and if we have a balanced chemical reaction, or a half reaction in this case, which has number of moles of electrons in it, then we're going to be able to play around with this a little bit and use Faraday's law to help us out to figure things out. The practical application here, you guys will start to see when we deal with some of the examples. You can see where we might be using these calculations in practical situations. So just a refresher here, this is Faraday's constant, 9.65 times 10 to the 4 coulombs per mole of electrons. And if you're worried about memorizing that, please don't. It is found here in your data booklet on page number 3, and it's right there. Faraday's constant, 9.65 times 10 to the 4 coulombs per mole of electrons. So that's there when we need it. We can then use this constant to convert electric charge into amount in moles of electrons. And so that's what leads us to here. Okay, is that if the number of moles of electrons transferred is equal to basically the charge over Faraday's constant. We're going to use this formula. If you want to memorize that one, that's fine. But we're going to use this formula here because it expands on the Q. So we see the I, which is the current measured in amperes, T, which is time measured in seconds, and Faraday's constant, which is coulombs per mole of electrons. And then remember that electrons, this is just number of moles again, in this case of electrons, is measured in moles. Okay, so that's where we're going with that. What we're going to do right now is to jump into the first example. So maybe get your pen and paper out, and what I'm going to do is I'm going to quickly transfer over to the next screen, the one that I want to, and hopefully you guys can see the example on here, and then I'll be able to write on this. Okay, so it says, what amount of electrons is transferred in a cell that operates for 1.25 hours at a current of 0.15 amps. Okay, so as we always do with our questions, I am going to just slide this over a little bit so you can see the paper. I'm going to write down what we know. So we know that we have a time of 1.25 hours. Okay, and we also know that we have a current of 0.150 amps. And what the question is asking us to figure out is what amount of electrons is transferred. Amount, remember, you should be thinking number of moles. Okay, so we're trying to figure out number of moles of electrons. The other thing we also know, remember please, is that we know Faraday's constant. It's a constant, we can always reference it at 9.65 times 10 to the 4 coulombs per mole of electrons. Okay, so how are we going to tackle this? This is what we're given, this is what we're required. We're going to assess how we're going to solve this. Well, we can figure out number of moles of electrons is IT over F. Okay, so then we can just substitute in our values here. One thing I'm going to do, remember time here has to be measured in seconds. So I'm going to just quickly convert this to seconds. And there are 3,600 seconds in 1 hour. Okay, so I can grab my calculator out and really quickly do that. I can do 1.25 times 3,600. Okay, and that gives me 4,500 seconds. Okay, and then I'm going to put that down here. So we've got our 0.150 amps, that's our I, times 4,500 seconds. Okay, there's our time, divided by 9.65 times 10 to the 4 coulombs. And then remember, if it's going to be per something, it goes up top here, per mole of electrons. So for those of you that are keeping score and want to cancel, remember that amp seconds, an amp second is the same as a coulomb. So an amp second cancels out the coulombs, and the units we're left with are moles of electrons. Remember, I'm probably going a little fast, and I'll remind myself to slow down a little bit. But you can always pause and rewind if you need to at any point. So then the last step we're going to do, notice how I put in here brackets. I want you guys to do the same just to make sure that we do the top first, then we divide by the bottom. So I'm going to do 0.15 times 4,500 divided by 9.65 times 10 to the power of 4. Okay, and that gives me an answer of 0.006, and then I'm going to check my significant digits. I've got 3,699 moles of electrons, okay, as my final answer. Okay, so hopefully that one made sense to you. And I'm going to quickly bounce back to our PowerPoint presentation and go to the next slide. Okay, so the next slide is our next example. So I'm just going to take this off, throw it on the floor, and move on to our second example. So this one is doing the same kind of idea, except that instead of looking for moles of electrons, we're actually looking for time. It says how long in minutes, so that tells us time, will it take a current of 3.5 amps to transfer 0.1 moles of electrons. So what do we know? We know we have a current of 3.50 amps. We have a number of moles of electrons equal to 0.100 moles. And we also, remember, we have Faraday's constant, 9.65 times 10 to the 4 coulombs per mole of electrons. Okay, and then what's the question asking us to figure out? It's asking us to figure out time. Okay, so next step then is, as always, we're going to go and we're going to figure out how we would solve this. So normally its number of moles of electrons is IT over F, but we're interested in T right now. So we're going to do a little simple algebra, okay? We got to get T by itself. So we ask ourselves what's being done to T at this point, and how do we undo it? Well, T is being multiplied by I. How do we undo multiplication? We divide. What we do to one side, we have to do to the other, and our I's have canceled out. Okay? T is also being divided by F. What's the opposite of division? It's multiplication. So we'll multiply by F. What we do to one side, we have to do to the other. Our F's are canceled. So T is number of moles of electrons times Faraday's constant divided by current. Now I can substitute my values. 0.100 moles of electrons times Faraday's constant, 9.65 times 10 to the 4 coulombs per mole of electrons. And then we have our current in here, which is 3.50 amps. Okay, on to the calculator again. Slide that over so I can see. We're going to do 0.1 times 9.65 second function 4, enter. So there's our top divided by our bottom, 3.5 amps. Okay, so that gives us an answer of 2,757.14 seconds. Okay, now I'm going to move my calculator and get rid of that shadow. It's asking for minutes up here. So then what we have to do is convert this to minutes. And we know that 1 minute has 60 seconds. Seconds cancel. So I'm going to take that number and divide it by 60. And that gives us 3 significant digits. I'm going to say 46.0 minutes. So to put this into context, if we wanted to transfer 0.1 moles of electrons at 3.5 amps, it would take us 46 minutes to do so. So hopefully that makes sense to you guys. If you need to pause at this point and go back, go right ahead. What I'm going to do is switch back to the PowerPoint, and we'll jump to the next step. Okay. So this next step here is dealing with half-cell calculations, and this is what's going to lead us into talking about stoichiometry and cell stoichiometry. So, since the mass of an element produced at an electrode depends on the amount of transferred electrons, that's what Faraday's law is telling us, a half-reaction equation showing the number of electrons involved is necessary to do our stoichiometric calculations. So there is that half reaction that we're going to need to have. So really what you should be doing at these points is dealing with these half reactions rather than dealing with a full net reaction, unless the question tells you otherwise. So this applies to both voltaic and electrolytic cells, but often we just worry about voltaic cells in these questions. And separate calculations must be done for each electrode if needed. But remember, the same amount of electrons passes through each electrode in a cell or group of cells. That last point is really key, is if we're worried about electrons passing, let's say from, well, it's always going to be from anode to cathode, whatever the half cell number of electrons transferred in the anode half cell is, it's going to be the same number of moles of electrons in the cathode half cell. Okay, so that's an important distinction. So what we're going to do now is we're going to move on to doing a calculation based on some stoichiometry. So we're going to start out as we always do. Step 1 is always going to be balanced chemical reaction. Maybe I should switch over to the feed. So step 1 is always going to be your balanced reaction. Okay, with your knowns and unknowns. I apologize for the atrocious writing. Okay. Step 2 is going to be number of moles of your measured. So that's going to be the thing that we actually know enough for to figure out the measurement. Step 3 is to figure out number of moles of your unknown. Okay, using mole ratio. And then step 4, as always, is solve for your unknown. Okay, so we'll set those 4 steps up and move from there. So in this question, it's asking, what is the mass of copper deposited at the cathode of a copper electrorefining cell operating at 12 amps for 40 minutes? In other words, the question's asking us, how much copper can we expect to be stuck on the cathode if it operates at 40 minutes for 12 amps? Okay, so that how much in this case is going to be what mass are we dealing with? So a couple of things stand out to me on this question. What is the mass? That is our unknown. Okay, so that's what we're going to be trying to figure out in the question. The other thing that sticks out to me is it's deposited at the cathode. What occurs at the cathode? Well, the strongest oxidizing agent gets reduced at the cathode. So why I'm pointing this out is when we get to doing our half cell reaction that we need in order to solve this question, you need to realize that we're dealing with a reduction reaction because we're dealing with the cathode, which is where reduction occurs. Okay? Other things we know in the question is our current is 12.0 amps, and the time is 40 minutes, which I'm going to quickly convert to seconds. So there's 60 seconds in 1 minute. Minutes cancel out, and that should be 2,400 seconds. Okay. And then lastly, we know Faraday's constant, which we're going to be working with throughout this concept. Okay, so that's what we know. I have a feeling I'm going to run out of room here, but let's write this down. So step one is balanced chemical reaction knowns and unknowns. Well, there's our knowns and unknowns over here. Now we need a balanced chemical reaction, and we're going to just do the reduction of copper, right? Because we're plating solid copper. Remember, this is solid copper over here. That's copper solution. We're plating solid copper or depositing solid copper on the cathode, okay, the electrode for the cathode, and it's going to have to be a reduction. So that means that we're gaining electrons, so electrons must be on the reactant side. That's step one. Step two, we can figure out the number of moles of electrons. Now that's the key here. We don't have a mass for copper, so we can't figure out its number of moles. There's no other information communicated about anything else in here other than these electrons. So we can figure out the number of moles of electrons by using IT over F, okay, which is going to be 12.0 amps times 2,400 seconds divided by Faraday's constant, 9.65 times 10 to the 4 coulombs per mole of electrons. Remember, an amp second is a coulomb, so they cancel out. We're left with moles of electrons. And so this gives us a value of 12, oops, let me turn this back on, 12 times 2,400 divided by 9.65 times 10 to the power of 4. Okay, so that's 0.298 moles of electrons. Okay, so hopefully that makes sense. Step 3, figure out the number of moles of our unknown using mole ratio. Our unknown is the mass of copper. Okay, and that sound was me running out of battery power for my phone, so I'm going to have to finish this question and plug it back in. That's the mass of copper. So the number of moles of copper, we're going to sort out using mole ratio the same way that we've done all the way before. So we have 0.298 moles of electrons times the ratio of what we want, which is moles of copper, what we have, which is moles of electrons. So there's 1 mole of copper for every 2 moles of electrons. Moles of electrons cancel. Okay, so my answer I'm going to just take and divide by 2. So it becomes 0.149 moles of copper. Okay, last step is going to be solving for our unknown. We want the mass of copper. Okay, so mass of copper is number of moles times molar mass. All I did is took this formula, okay, rearranged it to solve for little m. The number of moles is what we calculated up here, 0.149 moles, times our molar mass of copper, which you're going to refer to in your data booklet, the periodic table, which is 63.55 grams per mole. Moles on top, moles on bottom, cancel. So our final answer is going to be 0.149 or whatever was in my calculator, right? So all I did was I just took the answer and I'm multiplying it by 63.55. Okay, and that gives me 9.48 grams. Okay, so checking my significant digits, I have 3 sig digs here, 3 sig digs here. My final answer has 3 sig digs. Okay, so how much are we going to deposit for operating this cell at 40 minutes, or for 40 minutes at 12 amps? We'll deposit the equivalent of 9.48 grams onto that electrode. Okay, I am going to bounce back here for a second and pause while I go plug my phone in, and then we'll jump back in for example number 4. Okay, and I have gone and plugged my phone in, and hopefully that'll work, and I can dodge around the cord that's plugged it in right now. So I hope that last example made sense. Remember, if you need to pause, go back, rewind, or if I've gone too quickly, that's something you guys need to let me know. I feel like I'm going at the same pace I am in the classroom, but I don't know. Let's open that communication up with me if you can. So let's do the last one. And hey, look, that's the end of the slideshow for B, Unit B, which is a long one. Okay, so I'm going to switch back to our one last example, example 4. You can see the cord hanging down over here, so I'm going to try to tuck that out of the way so doesn't get in my way. So this is going to be relatively similar to what we did in the last one. We're still going to follow our 4 steps for stoichiometry that we always follow. And we'll sort our way through it. So first things first, silver is deposited on objects in a silver electroplating cell. If 0.175 grams of silver is to be deposited from silver cyanide solution in a time of 10 minutes, predict the current required. So we're tackling this one a little bit. We're going to run for 10 minutes. We only want to put on 0.75 grams of silver. Now, don't get confused on this question, okay? This is a silver electroplating cell. So what that should tell me is that our product is going to be silver, okay? The other hint that it's giving us to what kind of half-cell reaction we're dealing with is that it's from a silver cyanide solution. So remember that when we put an ionic compound in solution, it dissociates into silver ions and cyanide ions, okay? And it's really these that we're interested in. We're going to start out with those. So those silver ions are going to gain an electron, 1 electron, okay? And that's going to turn into the solid silver on the electrode that we're plating the silver onto. I hope that makes sense. What is the current required? That's what we're trying to figure out in the question. So let's take stock of what we know. We know that the mass of silver that we're trying to plate is 0.175 grams. Okay. We know that the time we're operating at is 10 minutes. Okay, I'm going to just quickly convert that to seconds because we need to remember that we're going to seconds with that. And there are 60 seconds in 1 minute. Let's cancel. So we're up to 600 seconds. Okay, we know Faraday's constant. Well, with electrons, and then what we're trying to figure out in this case is current. So this question is going to tackle things a little bit different than the last question did. The last question we started out with number of moles equals IT over F and finished with our number of moles is mass over molar mass. That's getting flipped here, and that's getting flipped because we're starting with mass already, and we need to figure out this unknown when we're done. Okay? So, and this is a balanced equation already, so our mole ratio is going to be super simple on this one too, which is kind of nice. All right, so that's step 1. Step 2 for this is we are going to figure out the number of moles of our measured substance. Because we have mass for our silver, we can figure out its number of moles. So the number of moles of silver is mass over molar mass, which is going to be 0.175 grams divided by silver is 107.87 grams per mole. Now that I say that, I'm just going to double check to make sure I said the right thing, because sometimes my memory fails me. No, I had it right. Okay, grams cancel out. We're left with moles. So I'm going to do, I'm not going to show you guys my calculator this time because I think you guys can figure it out. You hear me clicking away. 0.0016. Sorry, I lost connection. 0.00162 moles. Okay, that's step 2. Step 3 is to figure out number of moles of your measured substance, or your unknown, pardon. Well, in order for us to use this formula, we better have number of moles of electrons. So that's what step 3 is all about. We're going to figure out number of moles of electrons using mole ratio, because we can link these two together using the coefficients in that equation. So we're going to take our 0.00162 moles and we'll multiply it by what we want, and sorry, that's moles of silver. Multiply it by what we want, which is 1 mole of electrons, over what we already have, which is 1 mole of silver. So our ratio, there's 1 mole of electrons for every 1 mole of silver, and that is going to be the same number as we had before. Okay? Last step, we need to solve. We are not interested in number of moles of electrons. We need to get I by itself. So I'll undo division by dividing by T, and undo multiplication by dividing by T, and undo, so those cancel out, and we have to divide by T over here, and we'll undo the division by multiplying. Okay, so our current is going to be number of moles of electrons times our Faraday's constant divided by time. So it'll be 0.00162 moles times 9.65 times 10 to the 4 coulombs per mole of electrons. Okay, and then we're going to have our time in here, which was 600 seconds. Okay? All right, so then I'm going to go back into my calculator. Remember, I've already got that number in here. So all I have to do is go bracket, second function answer, and that just pulls that previous number in there, times 9.65 times 10 to the power of 4, okay, divided by 600 seconds. Okay, and we get 0.261. Checking my sig digs, yeah, okay, so this will be 0.261 amps. So if we ran this for 10 minutes at 0.261 amps, we could plate 0.175 grams of silver. If you wanted to be, if you wanted to make it run faster, to do the same amount, you could up the amperage, right? And it would happen in a lower amount of time. So in other words, you could put the amps up to 2 or 4 or 6 amps, and then you would end up with a much quicker solution to this problem. Okay, so that is all of the questions that we have. So I'm just going to bounce back to not there. I want to bounce back to here and just remind you of what you need to finish off for this unit. So now that we're done this video, we're just shy of 40 minutes. Sorry about that, guys. You can go on to LSM 14.4C, and the key's up in the Google Classroom to check that out. And then I'm going to post a couple of diploma questions for you. Just keep an eye out for it. And then there'll be a practice quiz ready for you as well to do that. Remember, with your practice quiz, always do it first. Well, do all the other stuff if you've got time. Double check with me to make sure you've done that stuff well. Do your practice quiz. Wait for feedback from me. Let me give you the okay, and then jump into doing your concept quiz for concept B10. So that's it for now. Thanks for paying attention. Hey, let me know how this new way worked for you. I hope it worked well. And if you have any questions, by all means, track me down. And hey, stay healthy, and we'll see you in Unit C, Organic Chemistry. Later.